All right. So for the person who's online, can you hear me? Okay, great. I have to ask, because I'm using the same mic for both OBS recording locally and also for Zoom, so I just need to make sure that the person who's online can also hear me. All right, excellent. So this time, I have already started the local recording, so I'm not using Zoom to do the cloud recording because of how it failed last time. And I think I might know why it failed because when I switch Wi-Fi, that might have triggered it to failed. So we'll see whether it happens this time or not. So I just switched to my router. So for the person who's online, can you still hear me? Hello? For the person who's online, can you still hear me? So maybe that's why it failed last time because when I switched to my local network, it stopped. Yeah, it's kind of interesting. All right, so let me so I'll ask one more time before I restart the Zoom. So if you're online, can you hear me? Oh, okay, good. So it's not because of that. It's something else. Don't know exactly why, but it just didn't work. All right. So, which is okay. I mean, all right. So I'm gonna roll back a little bit to what we talked about the other day, just because the recording was only partial and kind of quite partial at it. So, so let's go to Supernote. All right. So this was what I captured last time, and I'm just kind of presenting it here again. What you see in the rectangle, okay, so let me just kind of do this. So what you see in the rectangle, which is this portion here, that's iota. In other words, these are the well-formed formulae known to be true, okay, and you have to start with something. So as we explore the transformations, then we go like, oh, okay, if we have this particular expression and this expression here, then we can also come to the conclusion of this expression, and that's the transformation. The transformation, which are known as elements in zeta, they are completely mechanical and syntactic. In other words, we are not really looking at the meaning of implication or negation or conjunction or disjunction. They are nothing more than just symbols. So the whole point of propositional logic system, at least in this context, is everything is just mechanical because we want to mechanize reasoning. That's the whole idea behind this entire module is so that we can mechanize reasoning, so that instead of having us to prove a theorem, or to prove whether a condition, an expression is implied by iota or not, we want to have the computer to do it. Is that okay so far? All right. And so when we label this expression, then we can also label the other expression because using this particular transformation, we can also label this expression here. Once we have this expression, we can use another transformation to label this expression. And then once we have this expression, then we have another transformation to label this expression here, which is actually the end result. I just want to know whether not t is implied by everything that is in iota. And as it turns out in this case, it can be implied. So not T is a theorem of whatever I have in iota. Okay, so that's kind of a really quick recap of what we talked about last time. Do we have any questions about this? Yes, everything in the zeta has to do with transformation. So those are basically just mechanisms, that we can use to label um, well-formed formulae. So if I go back to the example, which is this one here, another example. So everything in Z is not a logical expression. Each one, which is from here to This one is only from here to here. The left-hand side of the infer symbol is a set of constraints, and if we can meet all of those constraints, then we can fire the quote unquote we can fire the rule so that the right-hand side of the inference can specify the pattern of the well-formed formula that we can also label. So in this one, it is kind of special because this is an empty set, which basically means there's no constraint whatsoever, which also means this psi here can be any well-formed formula. There's nothing special about this particular psi. It can be any well-formed formula because any well-formed formula or the negation of the same formula has to be true. And that's why we can label this particular OR expression regardless of what psi is bound to. In other words, psi can be any well-formed formula. So is that okay? Correct. So each element of zeta is a rule. The rule has a constraint or a set of constraints, which is on the left-hand side of the inference symbol. And if all the constraints can be satisfied by a particular way of using the Greek letters, then we can fire the rule, which means the right-hand side now specifies the pattern of a formula based on the Greek letters that can now be labeled. hmm Yep. No, it is not necessary for what we are doing here, but it represents one of the um, Boolean algebra rules. So, I'm just presenting it, just so that we know that, oh, there are really odd ones that look like that. But in this particular case, we did not need to use the first transformation rule. All right. Any other questions? Yes. Can I skip to the fourth? In other words, can we skip to this is the second, third, and this is the fourth? Well, it is in a set, so nothing is really ordered in a set. So that means all of these are available transformations, and as long as you can meet the constraints of inside the on the left-hand side of the inference, then you can go ahead and fire that rule. So there's no particular ordering to the whole thing. It is really just a matter of what is applicable. Yep. Um, yes and no. Okay. In So if you look at each transformation rule as a syntactical representation of a Boolean algebra rule, then yes. So each one is representing a particular rule in Boolean algebra. And as a result, you can kind of claim what you just said. Whatever is satisfied on the left-hand side is implying quote unquote, what is on the right-hand side, but the mechanism is entirely different. In other words, you can quite easily make a mistake so that your propositional system is no longer truly representing Boolean algebra. So the result of applying all of these rules is not valid. It's not actually representing, how we can do reasoning. Um, but the whole point is, this is mechanical. We want you to um, mechanize, the whole process of reasoning so that computers can do it, and they can do it in a much faster way than we can. Yep, go ahead. So um the discussion that we have here does not really address the question that you asked, which is about using a mechanism or an algorithm to decide which rule to apply when, right? And how do we expand the labeling of the well-formed formula. So that you're correct. We actually do not address that issue. One thing we can do is to go by what we call breadth first search, which means we just kind of use a kind of round robin way to go for, okay, is this applicable? Yes, go ahead, apply it, label something else, and then we just move on to the next possible rule. But the thing is, even with that approach, it is not going to work because if you have something like the first rule here, it can take on anything can be your your psi, which means there's no way you can actually order which one to go first because you have an infinite number of applicable well-formed formula to bind to psi. They don't because psi in this case does not have to be labeled or a part of something that is already labeled. Because if it has to be something that is already labeled, then you can kind of go like, oh, we at any time we only have a finite number of expressions that are already labeled. So you can kind of go like, oh, okay, there's a finite number to choose from. But in this case, your psi can be any well-formed formula, and there's an infinite number of well-formed formulas. So there's no easy way to go like, okay, which one should we use first? it and that's the problem, right? That is the problem of um, the propositional logic system as it is presented here, because as humans, you can kind of like go like, oh, okay, this doesn't seem to make sense. Okay, I'm not going to apply this rule because it doesn't seem to get me any closer to what I really want to prove. But when you're looking at a fully mechanized system, it's pretty hard to specify the heuristic to choose which one to expand first, and that's the problem. That's one of the main problems of using uh, this particular propositional logic system in order to automate reasoning. So my approach is to use the three things that I mentioned in the previous lecture. The first one is resolution. So are we ready to move on to just to continue to talk about resolution, or do we want to dwell on this a little bit more? Yes. Oh, okay. So let me see if the class is ready to move on to resolution. Are we all good? Okay. All right. So let's move on to resolution. So resolution, I'm going to do a quick introduction first, or reintroduction, because we actually talked about this last time. So I will do a quick reintroduction, and then you can go ahead and ask your question. So resolution is about this particular theorem. Okay, this is a theorem because this implication is always true. So that means anytime you give me a conjunction of two disjunctions, and of the two disjunctions, one has a component that is negated in the other disjunction, then I can always use this implication to get rid of that one component, and then we just kind of quote unquote concatenate what is left from the two disjunctions and just kind of put them together. Okay. Um. Oh. Okay. Okay. There we go. Um, and the whole point of this derivation, it is this part here on the right-hand side is the application of Boolean algebra. So this is all Boolean algebra based derivation. But the point is, this implication is always true. So when an implication is true, what it is really saying is if the left-hand side of the implication is true, then the right-hand side also has to be true. Okay, so that means, oh, so that means, wait, we can turn this into a rule in zeta. Because remember, zeta just includes all kinds of implications in Boolean algebra. So if there's an implication that's always true in Boolean algebra, we turn it into a rule in zeta. So as it turns out, this by itself is not terribly useful in logic, but there are two more components that will help us. One is called CNF, or conjunctive normal form, and then the second one is proof by contradiction. So we'll see how much of that material we can go over today, because with all three components, then we finally have a fairly, really, really mechanical system to prove theorems. Okay, so let me see if you have your questions. Correct. That would not be well formed, right? You typically, well, schemata usually do not get involved, in the actual expressions. So the way we use the schemata or the Greek letters is only in the when we specify a transformation. So they're only utilized as elements in elements of zeta because they're trying to specify a pattern. So that's basically what they're for. All right. So what we are going to do next is going to, so do we have any other questions about resolution? You see a pattern like this on the left-hand side of the implication, you basically just say, oh, we can simplify that. Simplification is always good. We are making things simpler. If you have three items and each item, so in general, resolution means, any one of these three items, phi, psi, or rho, each one can be a very complicated expression by itself. Okay, so there's no restriction as to what these what these Greek letters can be representing. So they can by itself, each one can be a very complicated Boolean expression. And as long as it has psi on this side and the negation of psi on the other side, it still applies. Is that okay? I just want to make that very clear. So resolution by itself is kind of awkward to look at, okay? And it's really difficult to apply resolution in general. So that's why we have to move on to talk about a new way of defining what is well-formed. So the new way of defining what is well-formed is we only have two operators left. And the way the two operators can stack is very specific. So we have negation and then we have or. There's no conjunction anymore. There's no implication anymore. And then we have this new term called is a disjunctive element. So basically everything in alpha automatically qualifies as an element in a disjunction, which basically means it can appear in a disjunction. Is that okay? So anything in alpha by itself can appear inside a disjunction. So that means 0, 1, PQ, RST, by them, each one can be an element inside a disjunction. The second one, says, oh, if you negate anything in alpha, that thing, the negation of that something in alpha, the whole expression can also be an element in a disjunction. Is that okay? And then the last one here is the most important one. So once we define what can be in a disjunction, then we say, oh, if you have a disjunction where every component can be in a disjunction, that disjunction is well formed. It can be seen as a well formed formula. And that's it. Okay, that's those are the rules. Okay, of how we now define what is well formed. It is a very restrictive kind of structure. Yes. No, we do not use quantifier. I'm only using quantifier here to specify, excuse me, the rule that we have to follow now. But quantifiers are still not a part of what we can prove. Yeah. All right. So I'm going to switch to the tablet here in order to give you some example of, oh, okay, Zoom just crapped out again. So let me go back into Zoom. I don't know why, but fortunately the recording is still on because I'm not recording to the cloud this time. I'm not counting on Zoom. So I have no idea why Zoom just keeps crapping out. Let me just go back in and, oh, okay. So unmute and then share. Desktop 2. Well, I lost the frame, so I knew that it was lost. Yep. All right. So getting back to this discussion. So let me go to a new page so that I can graphically show you what a well-formed formula looks like. Okay, this is all for my other class. All right, so now we're back to a new page. So now a new form, the new restriction of a new form of a well-formed formula is it has to be an OR. Now, what can be the components inside the OR? They can be any of the letters like P, Q, R, S, T. It can be a constant like a zero. It can also be the negation of anything in alpha. So, if Q is in alpha, then not Q can be one of the components inside a OR. And that's it. Okay, those are the only things we can have. So if we have PQRST 01 in alpha, then this is a well-formed formula. In other words, in a normal way, we would have written this as 0 or P or not Q or S. Oops. Uh, Back and back. There we go. Or S. So this is well formed. Anytime you see a negation that is not negating a variable or a constant, it is probably a problem. Okay. If you see negation, open paren something, probably is a problem. Okay. So are we okay in terms of what is considered well formed under the new rules? We good with that? Okay. All right. So now the next question is, um, what about CNF? Okay, CNF stands for conjunctive normal form. Where is the conjunction? Yes, go ahead. Okay, so can you give me an example where you go like, I'm not sure whether this is well formed or not, because I think it's better for me to evaluate what you think is well formed or what you think is not well formed. Then we can talk about that. Do you want to write something on the whiteboard? Okay. Yeah, because I think that's a better way to kind of evaluate, what you understand or at which level you're understanding the material. I'm not trying to put people on the spot, okay, but I am trying to, um, because when people ask me, they're not clear of what is well formed or not, that means in their head there probably are some examples of, okay, I have this expression, but I'm not sure whether it is well formed or not under these rules. So with an example like that, I can clarify and reference back to the rules that we have specified and go like, okay, according to these rules, this one is well formed or this one is not well formed. um, it's just a better tool for me to explain a concept or not. um, all right. Any other questions? Yes, correct. Because each and every one of the components inside the OR is either by itself from alpha or it is a negation thereof. The new rule is just that. Okay. Yeah. Anything, only expressions like this are quote unquote well formed now. There's because conjunction is not even one of the operators that we support. Yep. Okay. All right. So now the next question is, so what about CNF? CNF, the C stands for conjunctive normal form. So where's the conjunction? There's no conjunction in the well-formed formula. And then you go like, how is that? How does that work, right? So the way that works is if you think about, okay, so let's just say that this is, this space here is the space of well-formed formula, okay, under the new rules, okay? So you can have P or Q, as a well-formed formula under the new rules. You can have, S or not T as a well-formed formula, right? You can have PQR, okay, so R by itself. Okay, if you don't like R by itself because it doesn't have a conjunction, I mean disjunction, fine. Happier now. It is now a disjunction, okay? But it really just means R, right? So let's just say that these three are true, okay? They're in iota, okay? But these are implicitly ended together. In other words, everything that is labeled in the space of well-formed formula, they are implicitly ANDed. Okay, there's an AND across all of those because they're all true at the same time. So I'm just going to pause and make sure that we absorb that particular sentence. Everything in iota are true at the same time. So there's an implicit and across the expressions that are labeled. Yes, the conjunction is implicit. Yes, the conjunction is actually implicit. So that means if these three are labeled within the space of all the well-formed formula, we actually have a CNF now because the actual representation is this thing and this thing here and this thing here. That's the meaning of having these three items labeled, in the space. This is, basically the CNF that is implied by the three items that I have circled in the space of well-formed formulae. So let me go back to the question here. Not necessarily from the iota. I'm just saying that at some point we can label these, but basically all the things that are labeled already, they are implicitly in a gigantic conjunction because they're all true at the same time. All right. So are we okay now? Are we associating the labeling of formulae within the space with the implicit conjunction between the things that are labeled within the well-formed formula space? Because once you label something, we are basically, oh, we know this is true, but it is true at the same time as all of the other ones that are also labeled at one point or another. So are we good with that concept? Because that's a really, really important concept. Are we good? All right. So getting back to the notes, now we have this big question of, can we really express every possible Boolean expression under the normal circumstances as a CNF? That's a question, okay? And the answer is yes, we can. But then the next question is, how do we do it? There are two ways to do it. One is very mechanical and it will give you something that's going to give you a headache. The other one is to go through Boolean algebra and you end up with something that probably is easier to get to the answer. So it kind of depends on how you want to do it, but there are two ways to do it. Um, so to get to the completeness of CNF, I can do this in several ways. I can bore everybody to death, including myself, by reading what I just wrote, or I can use an example. You guys can give me a general uh, Boolean expression. You can have implication, conjunction, disjunction, negation in any nesting, and I will do it and I'll convert it into a CNF. I think that's a better way to do it. Okay. So does anyone want to give me a Boolean expression to turn into a CNF? It can be anything, and that person probably want to do it on the whiteboard because normal English, cannot express nesting very well. So unless you want to say open, open, open paren, blah blah blah, close paren, and open paren, blah blah blah, it's better to just to write it on the whiteboard, and then I will transcribe it onto the tablet. Okay, so who wants to give it a try? Okay, nobody wants to give it a try. Fine. Okay, go ahead. No, no, that's the whole point. The whole point is I can convert anything to the new format. Yep. So do you want to give it a try? Okay, go ahead. Yeah, yeah. Go ahead, write it on the whiteboard, and I'll transcribe it onto the tablet, so it's going to be recorded in the lecture. Just use any one of the five. You can use any combination of the five PQRST. And I can teach you guys how to write a program to generate a random, expression like this. Have you guys started to talk about trees in CISP 430? Not yet. Okay, it's not a problem. Huh? Okay. Um, I can still describe it. Okay, I can still describe the process of how to do it by hand, even though we cannot kind of code it into a recursive algorithm because you guys have not covered trees yet. Yeah, give me something challenging, like with a negation of and or negation of an or. This is not going to be one of the Steven Seagal demonstration of what's his martial arts style? Aikido. That's right. Yeah, because there are some videos of him demonstrating Aikido, where he's just people are just falling on their own without even Steven Seagal touching them. It's like, wow, that is okay. So let's work with this. Okay, but before we work with this, let me show you how you can kind of, because I think you might want to be able to generate random expressions just for practice purposes. Okay, so I'm going to describe that first, and then we'll transcribe what is on the whiteboard and work with that. So, let me go back to the tablet screen here. So the way you do this is to keep an inventory of the operators that you can have. So what operators do we have under in a normal kind of quote unquote normal expression? We have implication, we have or, we have and then we have negation. Okay, so those are the four that we typically use. Yes, we also have if and only if, but that can also be just be translated into a conjunction and two implications. So typically we work with these four. So what you do is you get a random number generator. You just say, okay, this is zero, this is one, this is two, this is three. Throw a dice, okay, and then you just go like, oh, okay, we got a two, fine. You put a two here. So now you construct a tree with two branches. Okay. And then for each node here, you also do the same thing. Now you actually have a fourth one, which is going to be a variable. Okay, so you throw a dice, okay, again, and this time let's just say that, oh, okay, it landed on the three. So it's a negation, okay, negation can only take on one operand. In this case, okay, let's say this is an implication, which also takes on two operands. Are you guys getting how I am populating this tree kind of randomly? Okay, so now you go like, okay, let's just do it one more time. Like this is an or, and oh, excuse me, it's an and, and the and is after a no, the not is operating on the result of an and. Okay, there we go. Let's make it an or. Okay, like that. Okay, so let's just say that all of the dangling ones are leaves. Okay, they're all variables. So in other words, the dice hits a four for all of these spots over here. So now, if it's a variable, then you just go to the variables that we have, which is P, Q, R, S, T, and then throw the dice again and randomly just pick these things. So you can say, just go like, oh, this is Q, this is a P, this is a T, and this turns out to be S. So now we have an expression which is not Q and open paren the negation of P or T implies S. Okay, so this is totally something you can do, with just a simple random number generator and a piece of paper. Are we okay? Does anyone have any question about how to randomly generate an expression so that you can have a chance of practice? Not a question? Yep, go ahead. Well, these are the operators that we support, and you can also have a variable which is not an operator. So that's why we have five options. But once you land on the variable, then we have the five variables in this case, because P, Q, R, S, T are all in alpha. I don't know what you're looking at on the screen, so I cannot tell where you're referencing. but then the class cannot see it. So basically, any point within here is just a random operator that we choose from the set of operators that we can have. Is that okay? All right. Okay. So, I'm just trying to describe a mechanism so that you guys can practice, the kind of thing that you probably want to have some practice with. Okay. So now we get back to the one that it was given to me. Okay. So we have this P and S. Okay. Or T and uh, U is not part of the. We'll change it to R. Okay. Fine. And then the whole thing implies T, oh, the negation of T and Q. Okay, there you go. All right, so now the question is, can we convert this into a CNF? Can we convert this into a conjunctive normal form? Okay, and if so, how do we do it? What is the process of doing it? So to do this, I'm gonna have to put on my funky looking glove because otherwise my palm is gonna touch the screen and kind of smear, you can change the zoom ratio and do all kinds of stuff that I don't want it to do. So there we go. All right. So I'm going to rewrite this, using the kind of simplified version. Okay. So because I'm used to it. So this is P or S. I'm just using the plus symbol to represent or. Um, oh, I take it back because that's not supposed to be or. That is supposed to be an and. Okay. So that is my mistake. So PS, if it looks like a multiplication, it is a conjunction. So now we have RT over here. I just want to keep things alphabetically sorted. It just makes it easier for me to notice things that can be simplified at some point. And then this entire thing is going to imply the negation of TQ, so QT, because I want it to be alphabetically sorted. So do we have any questions about this kind of simplified version of expressing exactly the same thing? Okay, yep. Uh, because this makes it easier for me to look for patterns and look for things that can be simplified. Because if I always use the alphabetical order, then I can notice QT and TQ being the same thing more easily. So it really is just for me to more easily notice things that are related. All right. So the first thing that I always do is to apply the definition of implication. In other words, A implies B is the same thing as not A or B. Okay, so that's usually the first thing that I do. So now in this case, it means I just have to negate the entire thing on the left-hand side of the implication. So now we just have PS or RT, negate the entire thing, and then do an or with whatever is on the right-hand side of the original implication. So are we doing okay so far with this part? Okay, this is by definition of implication. Okay, so when did we learn about the definition of implication? The first class. Yes, so we learned this the first class. Okay, so I hope you wrote some notes about all of that stuff. Because when you write notes, the process of writing the notes is one chance for you to kind of have that information to pass through your mind to kind of remember that. And also, now you have it on in your notes, and the chances of you locating something useful in your notes is much higher than locating the same kind of information in my notes because you're not organizing things the same way that I do. All right. So now we have taken care of all the implications. Now we can apply De Morgan's law. In other words, every time you see the negation of an and, or every time you see the negation of an or, you apply De Morgan's law. Because the only thing we can end up negating in the CNF are variables, individual variables. So if we're negating anything other than an individual variable, you have to apply De Morgan's law. One way to look at De Morgan's law is you are distributing negation to the inside of other operators. So it is a quote unquote a form of distribution. Let me kind of explain that a little bit. So negating A or B is the negation of A and the negation of B. Okay. So in a way, you're distributing because you're now saying, oh, we're not negating an operator anymore. We're now negating the components of the original operator, which was an OR. But now we have to change the operator from an OR to an AND. In other words, there's an implicit AND here. What looks like multiplication is conjunction. So that's why De Morgan's law is really helpful. You basically just say, okay, whenever I see the negation of an operator, apply De Morgan's law. Okay, so now we have quite a few places where De Morgan's law can apply. So see how this negation is applied to this OR over here. So I can apply that now. So I can now say I apply negation to P and S, but then I have to change the OR to an AND. So now we turn that into something like this. This is also an OR. Okay, so I just want to put extra parentheses to make sure that we get the order right. So this one is also a chance to apply De Morgan's law because we have a negation of an AND. So that turns into not Q or not T, like so. Are we doing okay so far? Yes. Okay. All right. So now we look at this and go like, can we apply De Morgan's law anymore? The answer is yeah, we can still apply De Morgan's law because this is a negation of an AND. This is also the negation of an AND. So I'm going to apply De Morgan's law to each one of these. So this one becomes not P or not S. We keep this AND, so this AND is still the same. And then this one becomes not R or not T. And then now we have the whole thing or not Q or not T. So I'm getting rid of this open paren and this particular closed paren here because when you have, because OR is kind of like addition, okay? The rule of association applies, which means you can dissolve the parentheses if you just have a whole bunch of nested ORs. Is that okay? Does everybody know what I'm talking about? The associative law in normal algebra, okay? So now we look at this and go like, okay, what can we do now? I think, oh, okay, I have one extra close paren that doesn't need to be there. So let me get rid of that first. We'll get rid of this guy. There we go. Okay, so now we can apply distribution. Okay, when you look at this, you say, oh, we can do FOIL in normal algebra. Guess what? You can do FOIL in Boolean algebra as well. But the question is, do we want to do that? The answer is probably not. Okay, so what I would do instead is to reverse one of the steps. Okay, so I'm going to group these two together again. Okay, which goes like, oh, but Tech, you just dissolve those parentheses. Why are you adding it back? Because there are two rules of distribution in Boolean algebra as opposed to only one in normal algebra. So let me on the side here describe the two distribution. So if you have A and B or C in Boolean algebra, you go like, oh, okay, I know how to do this in normal algebra, and it turns out to be the same thing in Boolean algebra. It works out the same way, okay? But in Boolean algebra, the other one also works. So if you have A or B and C as a whole, you can now combine this to become A or B and A or C. Is that okay? It looks awkward because it doesn't work in normal algebra, but it does work out in Boolean algebra. How do you, okay, so let's just say that you look at the second rule of distribution in Boolean algebra and go like, oh, that just looks awkward. I don't think so. Okay. So what are you gonna do? Hmm? Say again? Prove it exactly. Okay. You can do it now. Okay. What is the tool that we can use to prove the second distributive law in Boolean algebra, being that one? Truth table, exactly. Yes, I hope you guys are getting bored by that term truth table by now, because if you're getting bored, it usually means you're getting it. Not always, but usually. Okay. So, yes, we can prove. that the distributive law, the second one, actually works out in Boolean algebra. Okay, so now we look at what we have here. The objective is to have a CNF. Okay, so what we'll do is we look at the second distributive law and go like, okay, how do we apply that? Let me see. I think the one thing that is outside of the conjunction, we'll say that this is our A, and then we'll say this is our B, and we'll say this is our C. In other words, all I'm doing here is to show you, in order to apply the distributive law over here to the problem that we have over here, this is how we can do it. Okay, so now this just becomes an algebra problem because now we just have to say, oh, okay, so whatever A is, we just have to, add it to the disjunction already in B. So B is now, so I want to keep everything sorted. So now we have not P or not Q or not S or not T. This is by distributing A to B, which is, basically making this one over here. Um, and then we have a conjunction. The conjunction is staying. Okay, so whatever is between B and C stays, which is the conjunction. So now we are basically combining this to this. So we have P, Q, R. Okay, so Q goes first, and then we have not R, and then we have two not T's, which is combined into one because not T or not T is just not T. How do we know that? Okay, so we're basically saying A or A is just A, which looks awfully strange because in normal algebra that doesn't work. But remember, what looks like an addition is a disjunction. Okay, so how do we prove that A or A is just A? The truth table again. I mean, one or one is one. Yes, true or true is true. Yes. Okay. So now we look at this and go like, I think we're done. This is a CNF already because we have a conjunction of disjunctions, and each disjunction only consists of either variables or the negation thereof. We're done. Yes. Say again. We converted what was a more complicated thing that has the negation of an and, the implication, the or of ands and blah blah blah. We convert this entire thing into a CNF. Is that yeah? Say that one more time, please. We are still involving the same variables. We are just changing the format of how the same thing is expressed. Right. Those are the rules of Boolean algebra. So everything that I put on this side are rules of, or some of the rules of Boolean algebra. I mean the complete list is somewhat long, but mhm. It's pattern recognition. So the way I recognize that by the time I get to this, I can use this particular distributive law to turn the whole thing into a CNF. That's just looking at all the applicable rules and go like, okay, does this move in the direction that I need it to go? Because the other way is to apply a FOIL on this one. But if you apply a FOIL on this one, it's going in the opposite direction of what we want because you just ended up with a longer disjunction of conjunctions, which is opposite of what we want. So that's how, when you look at the rules that are applicable, you kind of have to use your kind of experience, okay, in some case, to look at this and go like, okay, I can apply this, but is this helping me to get closer to what we need? Which is also what you do with just normal algebra. It's just that the rules are similar, but not exactly the same as normal algebra. Yep. Okay. All right, so I have one question. Okay, with everything that I do in a class, especially if it is not prepared, you always want to ask the question of tag. You can go through a lot of these, symbol manipulation, but how do we know that the original expression, which is this one here, is actually equivalent to this one over here? So what is the answer to that question? A bigger truth table. Yes. So in this case, let's take a look at how many variables are involved. I think all five are involved here. P, Q, R, S, T. Yes. So we have all five your variables. So it means, if you want to do it by hand, you will need a truth table of 32 rows. Okay. Which is not undoable. It's just a lot of chore. So I do not imagine that you want to do it like that. Okay. So how do we do this without, having to do everything by hand? Well, we got a few ways to do it. Okay. One is to use a spreadsheet, which is my preference the way, because I just like to abuse a spreadsheet to do whatever I need to be done. Yes, I just said that. Um, the second one is, since using an Excel spreadsheet is not a prerequisite of this class, some people may complain and go like, but you didn't tell me that I have to understand how to use a spreadsheet to take discrete math. That question by itself is a little bit troubling to me because by the time you take discrete math, and you have to learn how to use a spreadsheet, and people complain about that, I go like, hmm, okay, well, I cannot say what is on my mind. Let's just leave it that way. Um, so fine, okay, we will not do this using a spreadsheet. Let's do it is with a C program. And then if people complain to me and say, but I only learned about how to use C++ and not C, I go like, yeah, but C is a subset of C++. What is a subset? We talked about it in this class. Okay, so let's go to use a C solution to do this. Okay, all right. So to do this, with a C program, let me switch to a command line interface. Which one is on? Okay, this one is in view already. Okay, so I'm going to reuse this one, and I'm going to have to shrink this a little bit so I can see the actual equations. There we go. Okay, so I'm going to say prove this. Okay, dot C. All right, so let's do this. Your other professors will totally frown at this program because I'm not going to practice any actual structured programming. I'm just going to make this as quick and dirty as possible. So I will have PQRST as local variables. So int PQRST, okay. And then we'll have a 5-level loop. So for p equals to 0, which is false, right? P is less than 2, which means I only want p to be 0 or 1 plus p. Okay, so this is how we do the first loop. Second loop, replace everything with q, and then to copy both lines, I'm just lazy. P, Q, R. Okay, and now I'm going to use regular expression because I'm getting even lazier now. Okay, substitute all occurrences of Q with, let's see, R, S, right? Okay, there we go. I think I need a G here because I have multiple replacement. And finally, T. All right, so on this line, we want to replace or substitute all occurrences of S with T and do a global, which means if there are multiple occurrences on the same line, you replace all of those. Okay, so now we have a 5-level loop. And if people say, but I'm a Python programmer, I can only interpret a program when it has the correct indentation. Fine. Happier now? Yes? Okay. I know somebody's gonna say something about that. All right. So the only time I'm gonna do something, that to parameterize the whole thing is to say, okay, int original, okay, and it has int p, int q, int R int S int T. Huh, okay, well that took me longer than I thought. Okay, so now I'm going to use original to capture the original expression, which is this one here. And then someone's going to complain and go like, but there's no implication operator. Okay, fine, we'll just define it ourselves, right? So, huh? Yeah, but I want to preserve the actual expression, right? So I will have, P implies Q, okay, int P int Q, and this is just going to return not not P or Q. Okay, there we go. So now we can actually use implication. So now we say the whole thing is an implication. The first thing, the left-hand side of the implication is um, P and S or T and R. Okay, so that's on one side of the implication. On the left-hand side, the right-hand side is the negation of T and Q. Okay, close, close. There we go. Put the semicolon. So now we have the original equation specified. And now we have the new one. I'm just going to call it CNF. It has the same prototype. So I'm going to, once again, be lazy, copy and paste, like so. I like VI. Yep, there we go. And if you disagree and you say you want Emacs, we'll have this discussion after class. And I'm not buying dinner either, because that's going to be a long discussion. It's the quickest way to start a holy war within the geeks, is to say, so what is your favorite editor? If one person says VI, you just have to say, I think Emacs is better. Instant war, instant war. Hmm? Well, my preference is Edline. EDLIN is a line editor. It's not even visual. VI stands for visual, which means it's a big step up from a line editor, which means you edit one line at a time, literally. All right, so now this one returns not P or not Q or not S or not T. And okay, this I know this part looks kind of boring because it really is boring. Uh, or not T, and put a semicolon here. Okay, so now I have two functions, to capture PKRST, or the original expression and the new expression. So now I just have to say if um, original PQRST. Um, all right, so this now we have a problem, okay? Because equal equal is not really the best way to do this, because equal equal implies that true is always represented by the same constant, which the compiler does not have to guarantee. So can someone tell me what does true mean in C++? If I have an if I have an integer value, but I'm using it in a Boolean context, what is true? Anything other than zero. Anything other than zero is true. So that means one can be interpreted as true in a Boolean context, two can be interpreted as true in a Boolean context, and so on. So every time you have a Boolean expression like this, okay, there's no guarantee that it has to use one to represent true. And there's no guarantee that it has to use a consistent integer value to represent true. In other words, sometimes if it chooses, it can say, I'm going to use 17 to represent true. And then the next time it would use, I'm going to use 3 to represent true. So that means you cannot really just do an equal equal to say that two Boolean values are the same when they are quote unquote Boolean. So now you got a few choices. Okay, you can coerce everything to just 0 and 1 and then do the compare. Yes, but this is regular C. It is not C++. There's no bool type. So instead of doing that, I'm going to use my favorite operator, which is the ternary operator. Because if you use a ternary operator like this, then yes, you can actually just compare them because I coerce the value of true and false to just 1 and 0 in this case. So question mark 1 colon 0, close, close. All right, so if they're the same, we're good. Oops, I meant to have a close brace here. Otherwise, they're not good. Okay. So because I'm using just regular C, I don't have C out, I'm going to use printf. All right, so here, this is good. Okay, printf, um, good. I know it is not very informative, but that's okay. And this one is going to say not good. All right. I think the program is all done. Okay, so save the program, gcc-g-o, prove this dot c. Oh, okay. I got a problem here because I got a. Oh no, I'm forgetting the zero. I'm forgetting to specify what to return in the else case. So let me go fix that. Do it again. It's all good. And if I run it, if I did everything right, okay, if I do the derivation correctly and do the program correctly, it should give me like 32 good. Okay, I think they're all good. Hmm? You have to count the lines. That's easy too. Or if you say, I want to make sure there's no not in each one, yeah, you can just, or, better yet, you can say, grab not. And if it gives you none, that means they're all good. So are we convinced that it is relatively easy to check whether two Boolean expressions are equivalent or not? Then you guys may say, but Tech, I think you just slipped in the little trick here. It always prints good. So I'm going to modify the program and intentionally sabotage the program and just say, hey, let's get rid of this not over here. So now they should not be the same. So we compile and then run the program again and grab not and go like, oh, okay, two of them are not matching. Now, I intentionally make this program not to be very informed when it tells me something is not good. So now the question is, without changing the program, how can I tell which test case failed? What tool should I use? I'm not going to change the source code, but I need to know which test case failed so that I can attempt to fix the problem. So what do we do? Yep, GDB prove this. Okay. Yep, okay. So what we need to do is to put a breakpoint on the printf when it says not good, which is on line 25. Run the program, and now it is at that breakpoint, which means it is about to print not good. So at this time, I can now say, okay, which test case am I using? What is P? What is Q? Whoops. What is Q? R, S, T. So now I know exactly which test case failed, and I can then use this information to go find out, okay, where did I mess up? Is that okay? All right. So I'm hoping this is actually helping to relate this class kind of back to programming, because we are not talking about discrete math separately as a pure math topic. We are still trying to relate what we do in this class to programming. So, that means, we can use programming tools to help us evaluate whether the two expressions are equivalent or not. Okay, we can still use those tools. In fact, it makes sense to use the tools instead of having to evaluate those two expressions 32 times to make sure they are the same. Okay, that is just dumb. Yes, I just said it. It's just dumb. Okay, because when you have tools to make it more efficient, why do you do it the slow way? Yep. That's a very good question. You can see if the AI can actually, prove this, whether these two expressions are the same. I have not tried it. Okay, so you're more than welcome to give it a try. This is one reason why I teach, in-person classes where the tests are on paper. Yes. Hmm? If you're paid hourly and you do everything by hand like this, you won't have a job anymore. Your employer will simply say, "There's a way to make this faster," and you choose not to. You don't have to come back to work tomorrow. This is a cardboard box, and then call the security guard and go like, "Okay, can you escort this person out of the building in about 15 minutes?" I mean, that's really gonna what's gonna happen, especially if you are to become a software engineer or a developer. Efficiency is what your employer is going to look for. All right. And that applies to federal employees now as well. Yep. All righty. So, are we convinced that there are ways to convert any Boolean expression into CNF? So we got the second component done. Okay, we got the first component is resolution. The second component is CNF. Yep. Yes. Well, I mean, the answer is any expression can be. Yeah. So now the last one is proof by contradiction. Okay, so I'm not going to go through, we only got like 10 minutes left. So I'm not going to go through the actual proof of proof by contradiction. This is not proof by contradiction anyway. This is really just a corollary of the proof. So this implication is always true. Okay, this is the entire proof of this implication is always true. So what is the big deal of this implication? This implication says if P implies Q is true, then you can have a conjunction of something else, but apply it to both of them, and the resulting implication is still always going to be true. In other words, if P implies Q is supposed to be true to begin with, then P and R implies Q and R is also guaranteed to be true. It doesn't matter what this R is. Is that okay? Okay, so let me just pause and make sure that we understand what this implication means, because this implication is always true, which means, anytime you have an expression of something implies something, you can always add a conjunction to both sides. You're always, ending with the same thing on both sides. The resulting new implication is also going to be true. Are we good with this? So I'm not going to go through the actual Boolean algebra to why this is always true. We're just looking at this result here. So given this is the component, this is the corollary that we use, then we can now say, what if, okay, what if psi is representing the conjunction of everything in iota? What if phi is the theorem that you want to prove? Okay, well, if this implication is true, then we can always do an and blah blah and an and blah blah to both sides of the implication based on the corollary. Is that okay? We can choose anything, for the conjunction here. As long as we are using the same conjunction component on both sides of the implication, it should still work. Okay? So now I choose to say, oh, what about ending with not phi? In other words, psi is still representing the conjunction of everything in the set of iota. Everything that is given to you to be true, it is still representing that. Phi is still representing the theorem or the expression that you want to prove that is implied by everything in iota. But I am choosing to negate the theorem that you're supposed to be proving to end it with psi, and then on the other side to end it with phi. So now you go like, oh, but tech, phi and not phi is guaranteed to be false because one of them has to be a zero, right? Okay, fine, simplify to this. So what this means is if phi is actually implied by psi, then the conjunction of psi and the negation of phi is guaranteed to imply false. Okay, you go like, but what implication that is true can imply false? So you look up the truth table. Okay, once again, truth table. Is anyone counting the number of times I said truth table today? No? Okay, maybe I think in future lectures, someone's going to have a little counter in the note that's like check, 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 check. Okay, so I know this implication is guaranteed to be a true, okay? But since on the right-hand side we have a false, this implication is guaranteed to be true. What is happening on the left-hand side? If you look at the truth table, okay, in order for the implication itself to be true, the right-hand side is already known to be false. What do we know about the left-hand side? It also needs to be false. So this is the principle of proof by contradiction. Okay, if you want to show that psi implies phi, then you can invert. Okay, you can negate phi and then end it with psi, and you should be able to prove that leads to false. That's proof by contradiction. Okay, we got about 4 minutes left, so I'll give you an example, an easy example of how to apply proof by contradiction. Okay, some of you have heard this before because I kind of mentioned it in the unofficial office hour on Monday, but I'm gonna kind of talk about it again. So let's just say that tech is very lazy, okay, which I am, okay. I admit to being lazy. I don't want to use my time to do things that I really should not be spending my time to do, such as finding a pair of socks in the morning, okay. But in order to make it lazy, okay, I only have, let's say, two kinds of socks in my drawer. Okay, and the reason why I have two kinds is because when the first kind sold out, I could not find any more of those socks. Okay, so I now have two kinds of socks in my drawer, which is actually true. Okay, so every morning, okay, before I turn on the light, I just reach into the drawer and go like, oh, okay, I need to find a pair of socks, and I just need to take out three socks, and I should be guaranteed there's a pair. Does that make sense? Okay, prove it. So a direct proof in this case is kind of difficult, okay? It is not impossible. It is just a little bit difficult, okay? Especially if I tell you ahead of time, oh, I have five of these socks and three of those socks. So, yes, I lost one sock, in each category somewhere. Okay. So you can prove that by literally looking at every possible way of choosing three socks out of the drawer and actually prove that out of those three, two makes a pair. Okay. You can do it direct proof. But the proof by contradiction technique is even better because what you're saying is, oh, let me negate the theorem. What is the theorem in this case? The theorem is not the fact that I only have two kinds of socks. The theorem is if I pull three socks out of the drawer, I'm guaranteed to have a pair. That is the theorem. So you negate that. So once you negate that particular statement, what do you say? What are we saying? We're saying that out of three socks, I do not have a pair, right? So if I have three socks and it does not make a single pair, what does that imply? All three socks are different. I have three different kinds of socks in my drawer, which contradicts the statement that I only have two kinds of socks. End of proof. Is that okay? So that is the power of proof by contradiction. Okay, uh, certain proofs they are very difficult, not impossible, to prove by using a direct proof, but proof by contradiction works exceptionally well for those problems. Um, we are not meeting next Monday, okay, but I do want to give you guys a little bit of mental exercise to work on. I already gave you a technique to create your own random Boolean expression, so you can try to convert that into a CNF. Okay, just start with something simple. Okay, don't go all out, to make something that is like a tree that has like 16 levels. Okay, don't do that. Okay, limit it to about 2 to 3 levels. Okay. The second one is try to prove the pigeonhole principle. So I will mention this as the last thing today. The pigeonhole principle states that if you have more pigeons than there are pigeonholes, okay, when all the pigeons return, then at least one pigeonhole is guaranteed to have more than one pigeons in it. It sounds really simple, right? It makes sense, okay? You have more pigeons than there are pigeonholes. So when all the pigeons return at the end of the day, then at least one pigeonhole is going to have more than one pigeons in it. Prove it. So I'm telling you that proof by contradiction is the easy way to do it. So I present that as an exercise for you guys to do over the break, over the short break. Okay, I really hate it when we have a long break and then immediately followed by a short break. You know, but that is the schedule. So I will see all of you next Wednesday. Have a nice weekend. And this time I have the whole thing recorded. Yes.